next talk by Kim Phai Mak from Cornell.
All right.
Yes.
All right. Thank you. First of all, I'd like to thank Nandini, Arun, and the organizers for giving me this opportunity. So I will be talking about some of our recent experiments on probing and controlling spins in 2D chromium iodide. We're from Cornell, and these are the people who actually done the work. Most in particular, Shengwei Jiang and Chenhao Jing actually did a lot of the experiments that I'm going to tell you. And boron nitride crystal from the famous Japanese group, and the chromium iodide crystal is from a Joshua Goldberger's group at OSU. I don't need much introduction because people already talk about it. It's a honeycomb lattice of magnetic iron with spin 3/2 and with a strong outer plane magnetic anisotropy. And also that is discovered by the University of Washington group in 2017 that the monolayer chromium iodide is a ferromagnet with a nice magnetic hysteresis if you measure optically. And turns out that when you go to the bilayer, it becomes an anti-ferromagnet. I think Peng Cheng also discussed that. It's actually only true that when it's in the monoclinic phase, if you apply pressure to go to the rhombohedral phase, it becomes a ferromagnet also. So it is a not only layer dependent, but also structure dependent, the magnetic ground state. And so from this simple measurement, we sort of know that the exchange energy scale from the temperature dependence, we know that it's on the order of milli-electron volt for the in-plane Heisenberg exchange. For the outer plane exchange, is weak. It's on the order of 0.1 milli-electron volt, and that is the reason that we can apply like a half a Tesla magnetic field to cause this spin flip transition. So the two-dimensional nature with this weak outer plane exchange interaction open up some possibility for us to control spins using a field effect device structure that I will tell you a little bit about in this talk. So this is sort of the outline. Sorry that I probably plan to talk too many. I have a long time not giving 10-minute talks. Just stop me anytime. Just tell me to shut up if I keep talking. So first I will be talking about controlling spins using an electric field. And then I will see that I will tell you how we can actually directly see critical spin fluctuations in 2 dimensions. And if I have some time, I'll talk about mechanical probes of 2D magnetism, and that actually open up a way to probe thermodynamic quantities in this monolayer of magnets. So first of all, in the bilayer chromium iodide in the monoclinic phase, it is antiferromagnetic. So it breaks the time reversal symmetry. And also, if you take into account the spin, it also breaks the spatial inversion symmetry because spatial inversion does not flip the spin. So since both of these symmetries are broken, you naturally expect that you have a linear magnetoelectric effect in the material. So simply speaking, naively speaking, if you apply a vertical electric field, you can transfer some of the spins from one layer to the other. And then because of stronger intralayer exchange interaction, and you will just flip the spin because of the strong intralayer exchange. So this is kind of magnetoelectric effect from electron transfer, and you expect it to be fairly efficient. So to really show that this effect exists, we make this dual gate device structure. So let me just tell you a little bit that we have a bilayer of chromium iodide sandwiched between hexagonal boron nitride, which is an insulator, and it's touched by graphene as an electrode, and then with the top and the bottom graphene gate. So we have 2 gates. We can apply an electric field through the material. We can also change the doping density inside the chromium iodide independently. This is a bilayer flick. This is the picture. You don't see the flick, but that's there. And we shoot laser beam at the material, and we modulate the left and right-handed light and look at something called the magnetic circular dichroism. And the signal actually probes the optical sigma xy, the optical Hall conductivity. And in this particular case, it's proportional to the magnetization of the sample. Okay. And this is the result. Actually, you can actually see that this is the MCD magnetic circular dichroism signal versus magnetic field, outer plane magnetic field. A zero electric field is an antiferromagnetic state with nearly zero magnetization until you reach a magnetic field that causes the spin flip transition. Then you prepare the system to a spin aligned state. But then when you apply the electric field, you can actually see that a gap opened in the MCD signal as small magnetic field and also as zero magnetic field. So the electric field generates a magnetization in the system. And if you, for instance, if you prepare the antiferromagnetic state in the up-down configuration, the magnetization just increase linearly with applied electric field. If you prepare it in the other time reversal configuration, the down-up configuration, it just decreases, or it goes to negative with increasing electric field. And if you align to fully spin polarized, you actually restore the inversion symmetry in the system, then you actually do not have a linear magnetoelectric effect. So I think all these are pretty consistent with just considering the symmetry of the system, and the effect is actually rather strong because you can actually see that the electric field at the highest electric field we can apply, we can change about, create about 20% of the magnetization compared to the saturation value. So it's a rather strong effect. And so I told you that we also have a dual gauge structure. Then we can not only apply electric field at a constant doping, we can also change the doping density independently from the electric field. For instance, this is with increasing electron doping. You can actually see that it starts from an antiferromagnet with a spin flip transition. Then the spin flip critical field actually decreases monotonically with increasing electron doping. And then finally, it actually becomes like a ferromagnet. So you use a gate voltage, you can turn the system from an antiferromagnet to a ferromagnet. This is quite interesting. We can actually take into account the depolarization field. We can extract the exchange constant, the outer plane exchange constant, as a function of the doping density in the system. And you can actually see that there is a critical doping that you have an exchange inverse transition, that the sign of the exchange interaction just changed this particular doping density. And yeah, and I don't know whether it has anything to do with these other terms of the in exchange Hamiltonian, but this is actually what we observed. You can actually create an exchange inverse transition with increasing electron doping. Okay, moving on to the.
In fact,
okay, yeah, cool. I probably can finish the second part of it. And I'll just tell you about directly seeing the spin fluctuations in 2D. As you know that when we get close to the critical point of a magnet, the mean field theory fails, and we have, the spin fluctuation becomes important. And particularly in 2D, the critical region actually expands compared to 3D. And this is actually a Monte Carlo simulation for the famous 2D Ising model. And it's a single domain. Actually, the black and the white means spin up and spin down. It's a single domain at temperature much smaller than TC. When you get close to TC, you actually see lots of spontaneous development of the domains, and they actually fluctuate in time. So if you actually plot the average magnetization as a function of time, when you get close to the critical point, they just fluctuate with large domains and at very slow time scales. It's just the reflecting the divergent correlation time and length at the critical point. Okay. So I'm not going to get to the details of how we actually managed to see the spin fluctuation, but I just want to acknowledge these two, Chen Haojing and Zui Tao, on developing a very fast and sensitive optical imaging technique that allow us to see the spin dynamics in real time. So here is actually a flake that is a monolayer magnet that actually prepares the spin up state, and this is the spin down state. The message I want to say is actually that we can enhance the optical contrast so much that even for a single layer spin, we can see actually 60% optical contrast. So you can actually get one shot of image and you can directly see it spin up and spin down in 10 milliseconds time scale. That's really limited by the camera. If we have faster camera, we can actually do faster. And so this is the image, the magnetization image, when we heat the sample from 18K to 26K, the critical point is near 22K. And so I just also play the video near the critical point. You can actually see lots of spontaneous. We're not doing anything here, actually, it's just everything spontaneous, the magnetization fluctuation inside the sample. This is flick, and this is another flick near it. And here it's still playing. You can actually see that when it gets close to the critical point, then lots of domain develop, and then it starts fluctuating also. And we are actually playing at probably 1/3 of the real-time speed, just to make the image a little bit more visible. Okay, so we can then from this image we can actually extract useful data. For instance, we can look at the magnetization at a certain point in space, and then when we go from the order state to the disorder state at high temperature, you can actually see that near the critical point, you actually get lots of spin fluctuations, spontaneous spin fluctuations in the system. We can calculate the correlation function using this data and obtain the correlation time scale. It becomes very slow near the critical point to about 1 second. And we can also actually apply a gate voltage to turn on and off the critical fluctuations. For instance, the black has no critical fluctuation, then we can actually apply some gate voltage, about 0.5 volt, to turn on the critical fluctuations. And that gives us actually some interesting game to play with. For instance, like Maxwell's demon, that if we want to switch the spin state of the system from spin up, then we turn on the critical fluctuations. And to watch it until it switches to spin down, then we just stop there, and then it goes to spin down, and we can just do back and forth like that. Okay, I don't know how much time I have. I have 2 more slides. So if I have I can just use 1 minute to tell about the mechanical detection of the magnetic state also. The idea is very simple. It's just that this interlayer exchange interaction is actually strain dependent. So that when the material makes a spin flip transition from the antiferromagnetic state to the ferromagnetic state, to the spin aligned state, the crystal actually expands or shrinks a little bit. This is known as the exchange magnetostriction. It reflects the fact that there is a spin phonon coupling in the system. So that if we actually can prepare a fully suspended device like this, and look at its mechanical vibration, then we can actually be able to see a small change in the strain of the system when the magnetic transition happens. And this is exactly what we see. For instance, bottom, we see the magnetic circular dichroism signal that reflects the spin flip transition for a bilayer chromium iodide. The top actually shows that the mechanical resonance frequency of this suspended device would just drop by a small amount exactly at this spin flip transition, because in the metamagnetic transition, the crystal expands a little bit. Okay, and furthermore, because now we can actually sort of probe the strain inside the crystal using this mechanical frequency, the time derivative of the strain is actually proportional to the thermal expansion coefficient, which is proportional to specific heat capacity. Then we can actually use this technique to actually measure do a differential measurement of the strain with temperature to measure directly the specific heat capacity, even for a monolayer of magnets, or in this case, it's a bilayer of magnets. So this is the measurement at 0 magnetic field. You can see this characteristic jump in a relative change in frequency, and that's actually consistent with quite consistent with the measurement of specific capacity for bulk chromium iodide. So, but this is actually done in just a 2 monolayer of this material. So with this, I just stop here, and happy to answer any question.
Thank you, Kinfai. Let's thank Kinfai for a great talk. Several questions. Let me start with the first one related to your talk. How thick is the graphene electrode?
Oh, I think I call it graphene. It's not graphene, it's few layer graphene typically we use, because that's just a little bit more convenient. Maybe 4 or 5 layer graphene, but exactly how thick, I think it doesn't matter. We can also use monolayer graphene. Yeah.
Mm-hmm. Then there are questions about spin transfer. When you were doing the electrical, when you were applying the electric field, is it like spin transfer or orbital magnetization?
We actually think that there are some spin transfer component if the system is doped. Okay, if it's not doped, then these are all bound charges, and the spin just cannot move between the layers. So that will only happen when you have some free carrier doping in the system. Without carrier doping in the system, then maybe a different mechanism is needed. So it would be more interesting. It would be interesting to actually map out completely the electric field and doping diagram to see like how much contribution is from this spin transfer and how much is from something else, right? For the magnetoelectric effect.
Right. Also, is there electron transfer in the plane? So does it become an in-plane conductor? This
yeah, whether I guess the question is related whether one can do some transport in the system. Unfortunately, the band is very flat. It's a 3D band, and there's also quite a bit of defect density in the material. So the electrons can very easily localize. I think the Anderson, the mobility edge corresponds to a very high doping density. So in the doping density range we can study is basically like a piece of wood. It just doesn't really conduct electricity. Yeah.
I see. And then do you expect the bilayer structure to change with the electric field?
Oh, good question. Seems not, because when we applied, when we do this pressure-dependent experiment, we apply pressure. We know that it changed from monoclinic rhombohedral from the Raman scattering experiment, and then there's a corresponding one-to-one correspondence between the structure, the interlayer stacking structure, and the magnetic ground state. And applying electric field, we don't really see the change in the ground state, but applying doping, we do see that it actually goes to like a ferromagnet. So maybe the interesting question whether it's there is a doping-induced structural phase transition between the layer that caused this transition. That we don't know, yeah, for that.
Mm-hmm. And then does the DM couple with the electric field? Does the DM in chromium iodide, intrinsic DM, induce polarization which couples with the electric field?
Maybe we need to do a electric field dependent neutron scattering, you know, otherwise I just cannot address this question. Yeah, we do not know. Yeah, we cannot really extract useful a number for the exchange Hamiltonian, right, from this type of measurement. I don't know how useful. We can measure some spin wave, but those are really like the gamma point frequency for the spin wave. We can measure it as a function of magnetic field and doping and electric field, but I don't know how useful that, maybe it's open up for discussion, how useful that is in terms of extracting some exchange constants. Yeah.
And maybe the last question, Peter, do you want to ask a question? On the time scale?
I guess I could, sure. That's a very nice idea that you could get out the time scales of the fluctuations, but the time scales seem anomalously long to me. You know, usually you'd expect some divergence that goes like a power law with the thing inside the power, your deviation, say from the critical point in temperature. So if you're 5% away, you would expect you know, a factor of 20 enhancement of some time scale from a microscopic time scale. So it seems hard to imagine you could get a second out.
Yeah, and actually we also measure not just this direct measurement, we also measure the AC susceptibility as a function of the frequency. And it's also really getting really slow near the critical point on the order of a hertz. So it does get really slow. And I think to really do some scaling analysis of the correlation time, maybe it's better not to do in this way, to do like the frequency dependent AC susceptibility measurement. I don't know whether we have done that to really see whether it makes sense in terms of the, you know, scaling analysis from the critical point.
Yeah, maybe I'm not even talking about something like scaling. I just mean like just the rough time scales. I mean, maybe some scaling is possible, but that, you know, people do scaling, and scaling is somehow always, you know, data always has enough noise that it always can scale. And I'm just kind of curious about just the very rough time scales. You know, 5% of the way from TC should give you a factor of 20 enhancement. And it's hard to imagine how you could get here hundreds of milliseconds.
So maybe we can discuss more on this. This was a lot of food for
interesting,
thought.
nevertheless.
Yeah, a lot of food for thought and very exciting talks. Let's thank all the speakers from the morning session. It's still going to be a morning session. The first morning session, let me say, Peng Cheng Dai, Hye Yang Ki, Indra Dasgupta, and Kin Fai Ma. Thank you.